Okay, good morning. Thank you, yeah. I'm going to get started. Okay, welcome. This is 15251, Great Theoretical Ideas in Computer Science. We have two instructors. I'm one of them. My name is Ryan O'Donnell. The other one's name is Bernhard Heupler, but he's not here this week. He's presenting his research on his great research on theoretical computer science at a conference in Washington, so he'll be here next week. I should mention that the class is being filmed, so if you don't want the back of your head in the video, then you should sit at the sides. But I think that only gets a few back of heads. Okay, so let's get started. So this is the first lecture. We're not going to do anything very substantial. I just want to tell you what the course is about and what we'll be talking about for the next 3 months. Okay, so the title of the course is Great Theoretical Ideas in Computer Science. I think it's a bit of an imperfect title. That's the one we're given. I would actually prefer just to permute the words slightly. It would be a bit better if it was Great Ideas in Theoretical Computer Science. And the reason for that is what we're going to be talking about for the next 3 months is exactly this topic, theoretical computer science. Okay, so that's what 251 is about. So, what I'd like to do in this lecture is tell you what theoretical computer science is, what it means, what we're going to study. We'll have to start by, trying to understand what is the definition of theoretical computer science. Just before we get there, we might want to warm up a little bit and try to understand what we mean by computer science. Okay. I suppose we could actually take it to the ultimate limit and try to decide what is meant by science. It's a deep question for this hour of the day. Well, let's just go back to computer science. We'll start from there. Okay, so what is computer science? All right, well, if you talk to somebody who's taking AP computer science or something, maybe it's like writing Java programs to solve problems. Okay, so I put this definition up here to mock it a little bit, but actually there is one part of this definition I like, which is solving problems. So it is true that computer science is about solving problems. But I thought I'd ask you. So what do you guys think? What does computer science mean? What is it about? Yeah. Writing algorithms to solve problems. Partly, yeah. That's a component of it. That's not maybe all of it. That's a good start. We're going to talk about that. Yeah.
Deciding what the good problems are.
Deciding what the good problems are. What's good? It's up to you. Yeah, that's true. It's definitely about problems and solving them. Yeah. Yeah.
Simulating a mathematical model in the physical world.
Simulating a mathematical model in the physical world. It's true that it takes place in the physical world. I agree. I don't know if the goal per se is about simulating a mathematical model. We're going to talk about mathematics for sure, and mathematical models will be involved. Yeah. Any other ideas? This is good. Last time, yeah.
Study of how we can use computers to solve problems.
Study of how we can use computers to solve problems. Yeah, that also, it slightly evades the question of what is a computer. Yeah, but that's a good point. Yeah.
Studying computation and abstract structures.
Studying computation and abstract. What was the last word you said? What was the last word you said? Structures. Yeah, that's pretty good too. This also is about, raises the question of what is computation. But these are all good. Yeah, you have something? Yeah, you guys are all really into math. I love it. So it's coming up in all the answers. It's great. Yeah, this is good. These are good answers. Last time we taught this class and posed this question, it was silence in the room. And it's you guys are all computer science majors, mostly. So I'm glad this class is on the ball. Yeah, so those are some great definitions. This is what I posed this question to myself. And it's how would I define it? It's my definition of computer science, science of computation. Done. Okay, of course that's cheating, right? But I like it. Actually, I prefer to, I switched it around, but I prefer to define computation, somebody else had mentioned this, rather than computers. It reminds me actually of this famous quote in computer science. It says, computer science is no more about computers than astronomy is about telescopes. It kind of emphasizes that, it's not so much computers as objects we're studying per se. This was said by one of the most famous computer scientists of all time, Dijkstra. Although in the interest of historical accuracy, he didn't invent it. He borrowed it from his friend. It was actually Fellows who first said this. But he's a pretty famous computer scientist too, so it's still inspiring. Anyway, back to our little story here. Okay, so I just changed the definition. I want to define for you the science of computation. And if I had to define it in as few words as possible, I don't know why I would insist on doing that, but there's only so much space left on this slide. I guess I would say computation could be described as the manipulation of information or data. Okay, and while we have science up here, I may as well say, okay, it's like the rigorous study of. So that gets it down to 4 or 5 words. Okay, so that's what I thought when I posed the question to myself. And I was like, well, let's check the answer. So I went to the ultimate source, Wikipedia. And this is what you see if you go to the computer science page, at least according as when I made these slides. Maybe somebody has changed it now. Okay, so this is how it starts. Computer science is a scientific and practical application to computation and its applications. So there you go. The science of computation. I nailed it. Then it goes on. It's like it's a systematic study of the feasibility, structure, expression, and mechanization of the methodical procedures or algorithms, somebody said that underlie the acquisition, representation, processing, storage, communication of, and access to information. In short, processing information. So yeah, that's what I said. Good. Maybe they kind of expanded upon it a little, which is nice. But okay, this seems like a reasonable consensus on what computer science is all about. I also want to highlight this word algorithms, which is mentioned. This is going to be something we'll talk about in this class, and indeed in the rest of the course. Okay, so let's take a look at these words a little bit more carefully and try to expand upon it. So computation, you can think of it as the manipulation of information or data. And an algorithm, which we're also going to talk about today, is the sort of the rigorous description of how the data is manipulated. Okay, so algorithm is like a piece of code or some instruction set that sort of tells the computation device what to do. This is the basic picture of computation. You have some kind of computer. I put it in quotes because it's some kind of computing device. And it gets some input and it produces some output by running this algorithm. And to get back to the Velociraptor comment, computational problem is what this whole process is trying to solve. And in a sense, the computational problem is like the pairs of inputs and the outputs. For each input, there's a desired output. And getting your computing device to achieve that output, given the input, is the computational problem. Okay, so I put computer in quotes because there are many different, physical mechanisms that can, do computation. So, a very simple one is like a calculator. I'm imagining not the fancy ones, but like the old-fashioned, desk ones that can do plus and minus and times and divide. And these do a limited form of computation, right? You give them some input, multiply these two 10-digit numbers, and they produce the correct output. Actually, you might try to think about how do they do it. It's not like they have a giant table of all possible pairs of 10-digit numbers. So it's doing some non-trivial algorithm inside the calculator to multiply these two numbers. Okay, so that's one kind of limited kind of computational device. Probably the most familiar one is like the laptop that some of you have in front of you right now. This is a sort of a general purpose computer. And what makes it kind of interesting for us is this property of universality. You can take a laptop and it doesn't just do 4 fixed functions. As long as you got a programming language on there, you can sort of do universal computation. You can write a program to do any kind of computation. You can write a program that is a little calculator app. You can write a program to sort lists of numbers. You can write a program to play whatever Plants vs. Zombies. You can have it do any computation you can think of. Okay, so this notion of universality of computation is something we're going to talk about a lot in the first part of this course. Now, these are not all the computational devices or mechanisms that we can think of. If you think of computation as this general notion of manipulating information and taking an input and producing an output, then in fact many things can fit into this box. And it's quite useful to take that perspective on a lot of phenomena. For example, humans operate this way too. Humans take input from their senses and they process it in their brains and they produce some outputs. And it's quite interesting to think about how computationally about how humans' brains do this or how human beings do this. Actually, just as an aside, if you look up computer in the dictionary, you'll see that actually it has 2 definitions. The first one is the one you probably think of as like a programmable machine that can, perform computations and calculations. But actually, definition number 2 is a human employed to perform computations and calculations. And again, if you look at like the etymology, this usage number 2 is like the real meaning of computer for like 300 years. Okay, that's what the word computer meant for a really long time. It wasn't until like the last 100 years when we had mechanical computers that, we tended to call this thing a computer. Okay, and actually, when we talk about the mathematical notions of computers and Turing's definition of computers, you'll see actually he was inspired by the notion of a human computer. And actually, these are some pictures of like the human computers that were active in his time. Actually, they're all women, as you can see. Okay, but back to this picture of computation as a process with information and then the manipulation of data and outputs. There are many other things that you can think of where it's beneficial to think of them from a computational perspective. So, I guess even getting smaller in terms of the human scale, you can think of a neuron and how it processes information and takes information and outputs signals. It's very interesting from the point of view of computational neuroscience. If you're interested in economics, you can think of markets as a form of computation. The inputs are everybody's preferences or the supply and demand. The market, operates, I'm told, according to some principles, and its output is, a clearing of the market or a steady state or an equilibrium for how the supply and demand is processed. So it's doing some kind of computation that's interesting to think about algorithmically. Or you can think of it, let's say, evolution as a computational process. The input is like some species, and some stuff happens, and some new species are output, possibly according to a randomized algorithm. And all these different topics or phenomenon, it's very interesting to think of them from this computational perspective. And indeed, I think this computational lens is like a great way to look at all sorts of topics in computer science. And one of the things that I really love about computer science is that, if you're a computer science major or a computer scientist, you can really study any topic you want, like any topic under the sun, biology, economics, astrophysics, chemistry, finance, whatever. It really benefits from computational thinking and looking at, the phenomena involved from a computational perspective. Okay, which is why, I'm really happy to be a computer scientist. I also kind of identify as a mathematician, but I would not want to only be a mathematician because, if you're a mathematician, you work so hard to study some like super weird topic like Frobinioids or whatever, and then like your whole life is just every day it's Frobinioids. But like if you're a computer scientist, you can just wake up and say, today I want to study economics, or today I want to study finance, or today I want to study biology. Yeah, so that's why I'm very excited when people are computer science majors. Okay. Well, that's the last thing I'll say about computer science. We've had like a nice chat about it now, and that's the general topic for the course. And now we're going to go back to the main subject of the course, which is theoretical computer science. Okay, so what is theoretical computer science? So if I had to define this with as few words as possible, or even like no words, then I might start with just a picture. So here's my picture to try to help define what theoretical computer science is. So this is computer science, and then this is mathematics, and then the green stuff in the middle is theoretical computer science. That's maybe the simplest way I like to say what it is. Although if you tell your friend or the person sitting next to you on the plane like you do theoretical computer science and show them this picture, they might still be like, what are you talking about? So I think there's actually an analogy that helps. It's an analogy with physics. I don't really know that much about physics, but I'm like a layperson to physics, so I think maybe it can help us understand the meaning of the topic. So if you think about physics, right, like, okay, let's draw the same picture, but like write physics instead of computer science, then again, like, you got physics and math, and the intersection is theoretical physics, okay? And indeed, I think it's the case that physics is divided, roughly into two parts. The experimental physics part, where you're building those lasers or like working on the Large Hadron Collider or doing, actual experiments. And the theoretical physics, which is the people who are basically doing, the math at the chalkboard that like underlies the, the laws of nature and the laws of physics. Okay, so these are people doing the mathematical models, your Einsteins or Hawkings or whatever. They're not firing the lasers. They're thinking about the math that underlies, fundamental physics. And it's the exact same situation for theoretical computer science, I think. We equally have some, heroes of theoretical computer science. These are all people that won like, the equivalent of the Nobel Prize for computer science. And they're doing the same thing. I mean, they're thinking about math as it relates to the fundamental notions of computation. And this is just as deep an issue. As we saw, computation and computer science touches on all aspects of science and nature. So it's really, it's an exciting subject to be thinking about these fundamental questions from a mathematical perspective. Okay, so just by the way, this is Shafi Goldwasser. She was an undergraduate here at CMU doing computer science. This is Manuel Blum. He's a computer science professor here at CMU. This is Avi Wigderson. Okay, not every single hero of theoretical computer science is here. We have a lot, but he's a pretty cool guy who's not here. And yeah, if you're interested, actually, I put some talks that these three people have given on the topic, broadly of theoretical computer science that you might enjoy looking at later. Okay. I have to put this slide up briefly. So, I kind of said that theoretical computer science is the intersection of computer science and math. I should mention that we're going to use it in a more limited sense in this course. This slide is like a technicality. In some ways, theory of computer science is divided into two parts called theory A and theory B. Theory A is algorithms and complexity, and that's basically what we'll be studying in this course. Theory B is another whole mathematical side of computer science that involves formal methods, logic, programming languages, and so forth. Even more so are all the heroes in this world here at Carnegie Mellon. Practically have all of them. But for the purpose of this course, we'll be talking about the algorithms and complexity side of things. Okay, and actually the letters A and B came from, in the 90s, they published these two handbooks of computer science, theoretical computer science, and they broke it up into volume A and volume B in this way. Okay. Right, so back to the discussion of theoretical computer science and its role within computer science. So again, I think we can look back to physics to kind of get some idea of the role of theory within computer science. So let's take a look at theoretical physics' role within physics. So we have the real world, and we have the abstract world. And we start in the real world, and in physics, they observe some phenomena. You do some experiments, you see some physical phenomena, and then you model it mathematically. So it turns out that the laws of nature are best modeled mathematically, and that, after having modeled the laws of nature, that takes you into the abstract world of mathematics. Okay, and then in theoretical physics, you explore the consequences of these models mathematically, and determine consequences for the real world. And then from these consequences, you can on one hand test the consequences experimentally and sort of refine this picture. And you can also get applications out of it, to engineering and practical, more practical concerns. And the story with computer science and theoretical computer science is very similar. Okay, so we have the real world, and computation goes on in the real world in many forms. On your laptop, your calculator, in your brain, in an economic marketplace, and so forth and so on. And we model it mathematically, and this sort of takes us into the abstract world of math. We explore the consequences of these models mathematically to derive new insights about computation. And then, ideally, we take these consequences and new ideas and produce, again, applications in the world of computer science and science at large. Okay, so this is kind of a picture of, what theoretical computer science is all about. So I actually want to talk a little bit more about this first part, the modeling of computation. And it's kind of an interesting story because another cool thing about computer science is it's a very young field. I mean, computer science is probably the newest, one of the most new disciplines, in any university setting. It's only been around for 60, 70, 80 years. And part of the reason for that is that this sort of step of really modeling computation rigorously was only done pretty recently, within the last 100 years. So I want to tell you a little bit about the story of that. We'll see more of it later in the course. So it's not like we haven't been doing algorithms in computer science for years. In fact, we've been doing algorithms for thousands of years. In some sense, maybe the most famous algorithm is this one, called the Euclid GCD algorithm. Possibly you've seen it before. It's a very simple algorithm. It's 3 lines long. And its goal is to compute the greatest common divisor of two positive integers a and b. And it's actually, despite being so short, if the two numbers are the same, that's the greatest common divisor. Otherwise, you subtract the smaller one from the larger one and repeat on 2 smaller numbers. Yeah, despite it being so short, it's actually got some quite deep aspects to it, which we'll study later in the course. Yeah, so this is an algorithm that's been around. Actually, it even predates Euclid. Again, in the interest of historical accuracy, Euclid did not invent this algorithm. It was invented by an unknown person a few hundred years before him. So not only humans as a species been doing algorithms for thousands of years, like you yourself have been doing algorithms since like grade school. I'm sure you remember this one. Addition. You learn like an algorithm in grade school to solve these problems, right? So this is the input, add these 2 numbers, and like they teach you, okay, you process the pairs of digits from right to left, 9 and 1. You have like a little lookup table in your head that's like 9 plus 1 is 10. Then you have to write down the rightmost digit, and you put the carry up here, and then you continue your loop in your head to the next pair of digits, 5 and 5, and you have to add this 1, etc., and you go through them like this. And you're actually running a quite sophisticated algorithm. And one that you all would probably have to think about it if you had to program a computer to do it on 1,000-digit numbers. Yeah. And then you progress through school and you learn some more algorithms. I don't know if this was maybe high school, probably. It's an algorithm for finding the real roots of a quadratic equation. Like the input is ax squared plus bx plus c. And then you compute this thing, b squared minus 4ac. And if it's negative, then there are no real roots. Otherwise, you output these 2 numbers. So these are quite numerical algorithms. We're going to be talking about non-numerical algorithms, of course, as well. But these are algorithms that you yourself have also been doing for many years. OK, so we've been doing algorithms for thousands of years, but we've only really had a formal mathematical model of what an algorithm is since about the 1930s, so 80 years ago. And it's an interesting kind of story. It all started because someone asked the right question. Okay, so sometimes in science, it's not, you don't have to come up with the great answers. It's enough to come up with the great questions. So I'll tell you a little bit about this story. The person who probably asked the right question that set the world on the path to defining algorithms and computation formally was this person, Hilbert. There are photos of him, but I put this drawing instead. So at the time in 1900, where the story starts, he's probably the most famous mathematician at the time. He's one of the great mathematicians in history. And it was 1900, so the turn of the century, and they're excited. And he organized a worldwide conference for mathematicians. So bring all the greatest mathematicians together so they could meet and talk about math problems. Sounds good. And he gave the most famous address at here, and the address was called "The Problems of Mathematics." And in it, he posed what he thought were the 23 most important problems in mathematics at the time. And he encouraged mathematicians to try to attack these problems. And he actually started by saying this. I'll read it to you. He said, "Who among us would not be happy to lift the veil behind which is hidden the future, to gaze at the coming developments of our science and at the secrets of its development in the centuries to come? What will be the ends towards which the spirit of future generations of mathematicians will tend? What methods, what new facts will the new century reveal in the vast and rich field of mathematical thought?" It's pretty good, right? That's a pretty good opening for a speech. It's kind of inspiring, and got all the mathematicians pumped up to solve his 23 problems. And indeed, over the next century, 22 of them were resolved. Still missing one. But I actually want to tell you, vis-a-vis computation, the story of his 10th problem, because this is the problem that sort of set in motion the mathematical foundations of computer science. So this was the 10th problem on his list. It's actually not exactly important what the problem was, but it was basically this. He said, imagine this problem. You're given a multivariate polynomial with integer coefficients. It doesn't matter. Set equal to 0, something that looks like this. And he said, mathematicians, devise a process according to which it can be determined in a finite number of operations whether it has an integer solution. Okay, so the point is, this part that's highlighted in yellow, he's basically asking for an algorithm. But they didn't really have the notion of algorithm. So he's like a process with a finite number of operations that, given this as the input, produces the output, whether or not, yes or no, are there integers x, y, and z that satisfy this equation. Actually, let me show you one of my favorite special cases of this problem. So a special case would be like find an algorithm that's given as input one number x, a positive integer. It's supposed to output yes or no depending on whether this equation has a solution in positive integers. This equation has like 28 variables. So you could think about that during the rest of the lecture. But it just has one input x that goes in here, and you're supposed to decide are there integers that satisfy this equation. So it's a tricky problem, okay? But this was his challenge to mathematicians in 1900. Come up with an algorithm for solving these things. So mathematicians went on, they started to think about that. They didn't really have any great ideas, to be honest, for a while. And 28 years later, he proposed actually a harder version of the problem. So like, let's step it up. And he was a German guy, so he called it this thing, Entscheidungsproblem. Just means decision problem. And here's like the harder version of the problem that he proposed. He asked mathematicians, given like basically any statement in mathematical statement expressed formally in first order logic, like this statement, devise and now he said effectively calculable procedure to determine if it's a valid statement. Does anybody know what this statement means colloquially? Everybody's mumbling. Yeah, this is a Fermat's last theorem. So is it valid? Yeah, it's valid. They proved it like 20 years ago. But it was very hard. So I mean, this is a hard problem, You have to take an algorithm, come up with an algorithm that like takes a statement like this and determines if it's valid or not. But again, forget the exact problem per se. What interests us more is, the command at the end. Again, it's asking for an algorithm, that takes this as an input and outputs yes or no according to whether it's a valid mathematical sentence. And really at this point, mathematicians got to think hard about like, okay, we should really rigorously define what it means an algorithm. Okay, so this was like getting towards the 30s. And several very noted mathematicians thought about this. So one of them was this person, Gödel. We'll talk about his more famous works later in this course. So in the 30s, he published some papers where he discussed some ideas for what it should mean mathematically to do computation, or what should be the mathematical definition of an algorithm. But he basically concluded by saying like, well, I don't really know. Like, here are some ideas I had. And then in 36, this person, Alonzo Church, who is also a great hero in computer science, kind of one of the founders of computer science, he invented something called lambda calculus, which is actually kind of like a weird programming language. Maybe you've even seen it before in some form. And he just asserted that I think this should be the definition of algorithm. Like, I think, the notion of an effectively calculable procedure is just whatever you can do with this lambda calculus. Which was an interesting idea, but like other people at the time, like Gödel and this other person Post, came back and said like, well, you didn't convince us. Like, there's no, I don't know, why this crazy thing you invented, why should that be the definition? Okay, so meanwhile, while all this happened in New Jersey, there was this British guy who was a graduate student who actually wasn't involved in any of these debates. He's a little hero of the story. His name is Alan Turing. He was 22 years old at the time. And he also wrote a paper defining a new model of computation. Actually, as I said earlier, inspired by the notion of a human computer. And he didn't call it Turing machine, but it became known as Turing machine after him. And it was a really compelling paper. You should read it because, I mean, after he wrote it, like everybody who read it, like Gödel, Kleene, even Church, were like, he nailed it. Like, it's extremely compelling. It's like a great definition. It's really a compelling definition. We should really adopt it as the mathematical definition of what is computation or what is an algorithm. Indeed, as like kind of a side note, 1 year later, he showed that his model of Turing machines was equivalent to this Church model of lambda calculus. Okay, and that really further bolstered people's opinion that like this was the right definition because, even though Church suggested this lambda calculus, he didn't really have a compelling reason, but now it seemed clear that, they hit upon the right definition. So we'll talk about this definition next week. Okay, and that led to what's called in computer science the Church-Turing thesis, which states something like this. Any natural notion or any intuitive notion of being algorithmically computable is captured by the mathematical notion of Turing machines, the mathematical definition of Turing machines. So kind of this thesis is turning an intuition or some kind of notion about the real world computation into a mathematical model. Now, this is not like a math theorem because although Turing machines are mathematically rigorous, I mean, this is an intuitive notion that it's talking about. So you might call it an observation or a definition or a hypothesis, or maybe you would call it a law of nature or a philosophical statement. But anyway, this is something that people believe in and proceed from, and that's what we'll do in this course. Okay, so with that in hand, we can look back at this picture I was showing you about the role of theoretical computer science within computer science. And we can kind of, roughly say that this first arrow here, taking the notion of computation in the real world and modeling it mathematically, is kind of captured by the Church-Turing thesis. Okay, and that gets us sort of into the world of pure mathematics, where we can reason mathematically about the notions of computation and algorithms. So I'm going to move on, but I just want to end this story. So go back to this Entscheidungsproblem that asked this question. Really to rephrase it, Hilbert was asking to devise an algorithm or a Turing machine, now that we have this mathematical notion, that given as input a statement in first-order logic outputs yes or no as to whether or not it's valid. And actually, I said that Hilbert asked the right question. This is not actually a question. It ends with a period. It's actually more of a command. Actually, he didn't really conceive of the idea of asking a question. The first question you should really ask before asking somebody to find an algorithm is there an algorithm? And Hilbert just assumed the answer was yes. But it wasn't a question that could be answered mathematically at the time because they didn't have a mathematical notion of what is an algorithm. So it was like up for debate. But in fact, once you've decided that you have a mathematical definition for algorithm, you can, before getting to the statement, ask the question, does an algorithm even exist? And the very surprising answer for Hilbert is no. This is pretty dramatic. This is proved by Turing that there is no such algorithm. There does not exist an algorithm that, given as input a first-order logic statement, always correctly determines if it's valid or not. Just sort of a dramatic way to resolve his problem, one that he didn't anticipate. And this shows the benefit also of rigorously defining things mathematically. It's not like Turing's word versus Church's word versus Hilbert's word. He had a proof, and we'll see this proof later in the class. Okay. And his easier problem, just to determine if an integer equation has integer roots, in the 60s, it was shown, even though this does not have, there's no algorithm to solve this problem. So that was shown by Davis, Putnam, Robinson, and Matyasiewicz. Okay, so that was the resolution of his 10th problem in the 60s. Okay. So now we talked a lot about theoretical computer science, and let's move on to not move on, but I'm going to tell you a bit more about what we're going to talk about in this course. So the course roughly divides into 3 parts. It's kind of like month 1, month 2, month 3, or topics of midterm 1, topics of midterm 2, topics of midterm 3. Yes, there's 3 tests in this course, and a final. Right, so the first part is about the things that we've been talking about so far. Formalizing the notion of computation, of algorithms, of computational problems, and how to reason about them mathematically. The second part of the course is about efficient computation, and I'll tell you a bit more about that, and basic algorithms and complexity. So let's see, what is this part 2 about? So part 1 is about computability of a problem. Given a problem, like given an integer equation, does it have an integer solution? The first thing you can ask about is its computability. Is there an algorithm that solves this problem? Yes or no? Well, sometimes the answer is no, as we saw, but most of the time, in most reasonable cases, the answer is yes, right? Usually when you get a computer programming problem on your homework, it's write a program that does this. It's not determine if you can do so. So most problems that you want to solve by computers can be solved. But you don't just end the story by saying, yes, it can be solved. The next follow-up question usually is, well, what's a good way to solve it? What is an efficient algorithm for solving this problem? And that's what the second part of the course and complexity in algorithms is really about. This notion of efficient, by the way, can be measured in more than one way. So the most frequent one you think about is efficiency in terms of time. You want an algorithm that solves the problem quickly. You can also look at efficiency in other measures, like want an algorithm that solves the problem without using much space, where space means memory usage. Some problems are solved by randomized algorithms. And it's an interesting physical / mathematical / philosophical question of where we can get real random numbers from. And so it's actually kind of interesting to treat randomness or random numbers as a resource as well, where you would prefer your algorithm to not use too many random numbers or too high quality random numbers if it can help it. So there's lots of different notions of efficiency that you can attack. We'll mostly talk about time, but there are other ones as well. Okay, and for each, one major activity in this world of complexity and algorithms is just studying this question for different computational problems. As we saw before, there's a whole world of computational problems, the basic ones you see in your computer science class, but also ones coming from, biology or finance or physics or whatnot. For every natural problem you want to solve, you can try to find the best algorithm you can for this problem. And this activity divides into two camps or two parts. The first part is trying to come up with efficient algorithms. Okay, you got a problem, try to come up with the best algorithm you can. And this is a problem attacked by algorithms designers. This is algorithm design. And the other camp, you might have thought about it a bit less in your life. It's what complexity theorists do. And this is trying to show mathematically that no such efficient algorithm exists. Okay, so as we've seen before, once you have the mathematical formalization, you can actually sometimes prove that certain algorithms don't exist. And these are kind of two competing camps. The ideal situation, the algorithms are, people are solving the problem better and better and better, and maybe the complexity theorists are showing, you can't solve it this efficiently, this efficiently, this efficiently. And the dream scenario occurs when they sort of exactly meet and they understand the fundamental complexity of a given algorithmic problem. How fast can you really solve it, let's say. And as I said, you can take this perspective and try to get these 2 points to meet for any computation problem you might be concerned with. I'll give you some examples. Multiplying 2 integers. That's the whole problem. The input is 2 integers. You output their product. There's a huge amount of work in computer science about the most efficient algorithm for this. We'll talk about that later in the class. It might not even really occur to you that there is an algorithm for this. There's the one you learned in grade school, right, where you write, again, it's like a more complicated version of addition. You have this tableau with the numbers, and you multiply them digit by digit, and then you do all this addition. That works. It's kind of a terrible way to do multiplication, as it turns out. It's very slow. And when you tell Python to multiply 2 1,000-digit numbers, that's not what it does. It also doesn't do the most efficient thing either. And we'll see people working on better algorithms for multiplication. And in fact, the fastest known algorithm for multiplication is not known. Fastest algorithm for multiplication is not known. So these two camps have not met up yet for even the most basic problem of multiplying 2 numbers. Okay, the inverse of multiplying 2 numbers is factoring an integer. Given an integer, think of it with like 1,000 digits, trying to break it down into prime factors. Here we don't really know very efficient algorithms, and it's sort of a life dream in computer science for camp number 2 to succeed, to show that there aren't efficient algorithms for factoring an integer. And indeed, all of cryptography, or most of cryptography, some of cryptography, a lot of cryptography is predicated on the assumption, which we could potentially prove but haven't, that there is no efficient algorithm for factoring an integer. And indeed, you rely on this assumption for security every time you type HTTPS into your browser. A problem involving factoring integers pops up, and the fact that you're shopping or whatever is secure is predicated on the assumption that there's no efficient algorithm for factoring integers. There's other basic problems in computer science, like sorting a list. You might think to yourself, come on, like n log n, that's done, right? Depends on your model exactly, as it turns out, and there are even open questions about the most efficient way to sort numbers. But there are other problems too that come up in a wide variety of areas. Detecting communities in a social network, DNA sequence alignment, computing Nash equilibria. All these computational problems, which are very important scientifically, there are open questions about what is the most efficient or what is the best algorithm for solving these problems. So that's what we'll be studying to some extent, these kinds of issues in part 2 of the course. Now, it's not just, a parade of like, here's a problem, let's try to find the best solution. Here's a problem, let's try to find the best solution. There are other like very beautiful open problems in the theory of computational complexity. I'll just mention a few. For example, does every problem with an algorithm using small space also have an algorithm that uses small time? So it's kind of space versus time, space and time for computer science. We talked about randomized algorithms a bit, and it's a very interesting question. There are many computational problems where we only know how to solve them efficiently with randomized algorithms. And it's a very interesting and unknown problem to ask, is it always possible to achieve the same thing with a deterministic algorithm? One of the questions I'm very interested in right now is whether quantum properties of matter can be used to speed up computation in a fundamental way. Talk about this a little bit in the class. And this P versus NP problem, which is very famous, we'll certainly be talking a lot about it later in the class and falls into this category as well. Okay, so that's part 2 of the class. And let's move on to part 3 of the class. Once we kind of sort of talked about the basics of algorithms and complexity, in some ways part 3 is a bit about highlights of theoretical computer science. And in particular, each of these highlight areas, it requires some new mathematics for you to learn. And so part 3 will in some ways be about different mathematical topics and how their impact for theoretical computer science. So, this is kind of a big picture course, especially towards part 3 of the course. We're going to be talking about all sorts of different, exciting topics in computer science, quantum computation and interactive proofs and cryptography, undecidability, and so forth and so on. And, by taking a look at these things, number theory or what have you, you can see that, we're going to need to learn some math in order to talk about these problems. So all these topics require some mathematics. And indeed, this is kind of, a running theme, not just for the last part of the course, but the whole course. I mean, part of the goal of 251 is to train you in mathematics and in sort of rigorous, logical, abstract thinking. So, I mean, we'll be doing proofs in this class. It'll be pretty mathematical. Right. So just to expand upon this a little bit, this was a picture I, put up before, sort of to explain theoretical computer science. And I want to expand upon it somewhat. So let me shrink this one down. Let me add another circle to this Venn diagram. Actually, I wanted to add 2 more, but it's quite a disaster. If you ever tried to draw a Venn diagram with 4 circles, it's a pain. So I rejected those slides. So let me put one more circle down. This is the circle of people who are computational thinkers. Okay, so this is how they overlap. And it's sort of a core belief here at Carnegie Mellon that it's important for all scientists to be in this giant yellow bubble. I mean, not everybody has to be a computer scientist, but let's say if you're a scientist, it's important to think about your work computationally. We talked about this earlier with the computational lens on other sciences. Okay, so that's the importance of computer science and computational thinking. Maybe for most of you, we're already at this stage. So for 251, maybe this bubble is more important, which is the bubble of mathematical thinkers. Okay, and it's also a core belief of us here at Carnegie Mellon in computer science that to be like an effective computer scientist, you really have to be at least in here, this like light green part. Okay. I mean, you need to be able to think about computer science from a mathematical perspective. So in some sense, goal number 1, or one goal of 15251 is, to finish the process or continue the process of moving everybody from this like yellow moon into the light green part, okay? To get everybody comfortable with and thinking mathematically about their computer science. Okay, this started in concepts, but we're going to continue it here. And maybe some kind of goal, this is not like a goal for everybody, but I mean, for some people who are really interested, hopefully we can get you interested in, getting all the way into this topic of theoretical computer science, which at least I like very much. Okay, so that's my pictures about mathematics. Now, It's a very important topic of this course. Mathematics of computer science. You're going to be doing like math for this semester. And I really wanted to explain it some more. I wanted to think of a metaphor for math and computer science. Kind of really hit home what I was trying to decide on or explain. And I came up with the following. Now, I don't know if this is going to work. This metaphor will make sense, but we'll see. I'll try it out. So to me, mathematics is like, cilantro. Now, bear with me here. This is my metaphor. There are 5 kind of people when it comes to cilantro. Okay, so category 0. Of course, the natural numbers begin with 0. It's very good to index with 0. So first category 0, is people who don't know what cilantro is. Okay, so it's this thing, Right, yeah. You may know it best as like the green stuff in the rice at Chipotle. Okay. Yeah, so, or maybe I'm saying it funny, like I'm from Canada, but I try to do an American accent. Like, we would call this cilantro in Canada. It's a herb in Canada. Anyway, this is, that's what it is. Yeah, maybe some people call it coriander, but I'm talking about the leaves, Yeah. That's how I feel about it too. We'll see. Or like, this is the wonder, do the glories of, this is what Google Translate tells me. I'm sure I got some of this wrong, You can send me your corrections later. Does anybody know for a fact that one of these is grossly wrong? Yes? Yeah, I knew the Chinese one would be totally wrong. Okay. You send me the fix later. By the way, this is still a metaphor for mathematics. Let's not get all right. Okay, so now I hope you all remember what this thing is, cilantro, right? Yeah, okay, so that's the 5, that's category 0, but now nobody's in that category, hopefully. Okay, the second category, number 1. This is the people who love cilantro, okay? They just love cilantro, and that's me. I love it. And you might be saying, like, wait, are you talking about math or cilantro? Both, okay? I love it. I love the math, love the cilantro. There's like tumblers for people like me that you love cilantro. Yeah. Some people really love it, okay? And if you're like me and you really love it, that's fantastic. Like, you don't have to love math. You don't have to. Not everybody does. But if you do, then I hope, like me and the rest of the staff, then we hope you'll really like this course because it's a course. It's a very mathematical course. Okay, that's the second category of people. Number 2, this is like the people who think cilantro is fine. Like, it's okay. Yeah, it's okay. I can eat cilantro. And maybe this is the biggest category. I mean, our dream is that everybody will be in this category at least by the end of 15251. I mean, you don't have to be officially a theoretical computer scientist, but we hope that you like it okay, you like the math, you can enjoy it. This is what I just said. Okay, we want everybody, ideally, to be able to think mathematically about computer science. All right, that was third category. Fourth category. This is the people who don't like cilantro. Now, here's the thing. Remember, it's still a metaphor for math, right? You got to try it, like eat your vegetables. And I'm going to try to show you like all the tastiest cilantro dishes, like all the most cool mathematical topics within computer science. And you're gonna eat it. And look, at the end of the semester, right, if you legitimately gave it a try and you still say like, I don't like cilantro, then fine. Okay, I can appreciate your position. But hopefully you'll still be able to like eat it like if necessary, all right? Okay. That's category 4. Okay, finally, the fifth category, last category. This is people with a genetic condition that makes cilantro taste like soap. Now, I actually don't know 100% where this really exists, okay? There's like these news stories, like, I don't know, 5 or 8 years ago that were like scientists discover gene, people like, it makes cilantro taste like soap to them. This is why they hate cilantro. I don't know. You can never trust these studies per se. Similarly, some people, mathematically say like, well, I'm just allergic to math. Like, I don't have the math gene. I can't do it. Again, I don't know if that's really true. I think you can do it if you apply yourself. And I sympathize, but here we are in this class. You're going to have to do a little math. You're going to have to try it. Okay, so actually on this last subject of people who are a bit allergic to math, I want to show a video that expresses some opinion about this. Hopefully it will be at the correct volume level.
Hi, my name's...
Let's increase the volume.
Hi,
Hello.
my name's Sarah Mora, and I'm a math major. It's true. I'm a math major. I study math on purpose. And what I really want to talk to you about today is the kind of reaction I get when I tell people I'm a math major. And I say, oh, I study math, I'm a math major. And I usually get responses like this. Oh, my brain's just not built for that. I'm more creative. Oh, wow. I'm just too slow at it, I just can't, I'm just too slow. I just never really know. It's genetic. Oh, I'm just not a number person. Oh, I hate math. Okay, so here's the deal. Math is hard. It is. We all know this. It's not like we go around speaking math all day and then can just switch in and out of it all the time. No. We have to stop and switch gears and change what we're doing, and that can be really confusing. It's as if we were having a wonderful conversation and then all of a sudden I stopped and asked you to write me a poem in Russian, and you don't know Russian, and so you have to stop and learn some basic Russian and then try to figure out what kind of poem I want. And maybe I'm helping you out, maybe I'm trying to explain what's going on, but there are some Russian words that don't really translate into English very well. That's really hard. And math can kind of feel like that when you're not used to it. In fact, math can kind of feel like that even when you are used to it. So nobody's expecting you to come into this world with every mathematical tool ever known to man fully formed in your brain. That's just not going to happen. So give yourself a little slack. No one's going to expect the right answers all the time. Okay, that kid in your class who just knows all the answers and is always raising their hand really fast and just makes everyone feel kind of stupid, right? Okay. Let's go back to the Russian poetry analogy. Imagine you're in a Russian poetry class and there's a kid in the class whose family speaks Russian. Or maybe they speak, Ukrainian or something, and that's really similar, so he has a leg up. Or maybe, she listens to a lot of Russian music and just really likes it, and so she's picked up a lot of stuff. Stop comparing yourself to that person. Seriously, stop. You have no idea what a student's background is. Just because they can answer something faster than you can does not mean that they are better than you. And it does not mean that you are stupid or that you don't know how to do whatever skill it is. It means that they're in a different place than you. That's really all it is. Math is a skill. Did you know that math a week ago? Do you know that math now? Do you at least know some of that math now? Anything is a big victory at that point. It's just like learning how to sing or dance or ride a bike or cook or something. You might make mistakes. You might find it's really hard. You might, fall off the bike. But that doesn't mean that you will never learn how to do those things. It means that right now you need more practice. So practice. Ask for help. Demand help. Talk to people who seem to know a little bit more than you do. Maybe they'll be able to, give you some advice. If that's too scary, talk to people that are on the same level as you and try to get a sense of what you don't know, and then go to your teacher. You can't practice if you're constantly talking yourself down. Math is hard, but you can do it. It's not magic. It's a skill.
All right. Well, it seems like a good place to end the lecture, but there's 20 minutes left, so we will not end the lecture there. But we'll go on to like the boring topics. So this is, this is the summary of what this course is going to be about. And I'll tell you about the logistics of the course for the last 20 minutes. Oh, I should mention that person, she now does robotics, so she's in computer science, in fact. Okay, right. Well, here we go. Course logistics. There is a web page for the course, as you may not be surprised to learn. This is it. Contains all the important information, the schedule, the times, dates, locations. The slides will be up there after the lectures. The videos of the lectures will be linked to up there. Hopefully there'll be notes, kind of lecture notes about the lectures sometimes. The homeworks will appear there, etc. Also appearing there are the course policies, which you should really read. I'm not going to go over them 100% in this lecture, but go to the web page and please read them. Feel free to ask questions about this stuff, by the way. Feel free to ask questions always, but here in particular, there's some details you might want to get straight. Okay, grading, everybody's most favorite topic. It's a relatively simple one this year. Homeworks, maybe the most important part of the class. There's 11 of them. Your lowest one will be dropped, so each one will be worth 2.5%. So I mentioned before there's going to be 3 midterms. I guess only this one is really in the middle of the term, but there'll be 3 tests, basically once a month. These are the 3 days, so please actually mark them on your calendars now. As you know, there's like another block of time besides the Tuesday and Thursday lectures and the Friday recitations. We have this Wednesday night session that's usually from 6:30 to 7:50 in Doherty 2210. But on the nights of the midterm, it's going to be extended till 9:30. So please clear your calendar for those extra 2 hours on these 3 days. There's an exam which is worth 25%, and participation is worth 5%. So what factors into participation is, to a great extent, lecture attendance, which we'll talk about briefly again later, recitations, attendance, office hours, piazza. Basically, don't be a ghost in the class. It'd be great if I know your name and know you personally by the end of the class. That's good for you. Definitely your TA should know you at least. Piazza, okay, this is the other important website for the class. Probably you've used Piazza before. This is like the bulletin board. We have questions and answers and announcements. If you have any questions about the homework, actually any questions about the course, your first line of action should be using Piazza, like as opposed to emailing staff directly. You can ask all your questions on Piazza. So using Piazza is mandatory. Okay, you have to sign up. You should check it every day, because this is also where we'll do announcements like there's a mistake on the homework. It should be changed to this, or other announcements about we have extra office hours here or there. So you should definitely check it all the time. We'll also be using it for a third purpose, which is in-class polls. Okay, so in every lecture we'll have 1 or 2 of these where we'll ask you a question and you'll basically vote on your answer using Piazza. We will in fact also use this as a means of taking attendance during the lecture. So you have to vote in order to attend the lecture. And we would like you to ideally do this on your phone, so you can go to the website, or there's like apps for Piazza. That's how we would prefer you to do it. The less good case is to bring a laptop and do it on your laptop. If you have neither a laptop nor a phone, we'll work something out. Let us know, but probably most people do not fit into that category. Please bring this like every lecture, because you gotta do the polls and thereby make your attendance known. We're actually going to practice this tomorrow. I'll mention that a bit later. Okay. Homework. So there's a lot of homework. In some ways, it's the most important part of the course. So the homework is meant to reinforce what we did in the lecture, also challenge you, expand your mind, try to get you to think more about the topics of the course. It also is the best way to prepare you for the exams. This is how you do well in the exams, is to do a thorough job on the homework. And the homework is difficult, so please make use of office hours. We're here to help you, so please take advantage of this. The office hour time should be on the course website. particular, I have office hours today if you want to come, from right after this class till noon, and also 1 to 2:30. Okay, so a little bit more detail about the homework. The format of the homework is maybe a bit different from in other classes. Firstly is we have 3 categories of homework problems, which will be clearly marked on the homework: solo, group, and open. Solo problems, as befits their name, you're supposed to work on them by yourself. Okay, so the maximum number of people that can work on this problem is 1, you. You can only talk about them with the course staff. Okay, these are solo problems. Group problems are problems usually harder. You must work on these in groups. It's not suggested. This is required. Groups of size 3 or 4. So, within this group, you can talk amongst yourselves about the problems. And you can also talk with course staff. And the final category is open, which you can discuss with anyone else in the class and also with the course staff. On the topic of groups, I should mention, you should start getting into them. Our first homework will be on Thursday. And there's like a mega thread or like a post on Piazza that you can use to try to find group members if you want as well. Okay, more information about the homework. So another unusual aspect of the homework is these Wednesday night writing sessions. So most of the time when you have like written homework, you write it up and you turn it in. But that's not how it goes in 251. So it's turned in a different way, and it's turned in a way such that we can be guaranteed that you wrote your solutions yourself. So that's what the purpose of this Wednesday night session is, from 6:30 to 7:50 in Doherty. So here's how it works. I mean, from Thursday, when homeworks come out, to Wednesday, you're solving the homeworks. Okay? And then by Wednesday, you've solved the homeworks. And then on Wednesday night, you write down the solutions to the homework problems with your hand and a pen, okay, on paper. Now, actually, there's not enough time in 1 hour to write down the solutions to all the problems. So we'll tell you some like random subset of the problems, and these will be the ones that we grade. Okay, so we'll remind you of the problems, although hopefully they'll be burned into your mind anyway on Wednesday nights. One brief exception here is that tomorrow is Wednesday, but there's no homework yet. So instead, if you want, I'm going to give, you don't have to come, but I'm going to give an optional lecture about proofs. And we can also practice the in-class polls if you want to get the technology of logging into Piazza on time correct. So that's what we'll do tomorrow. All the future Wednesdays will either be homework writing sessions or midterms. Okay. Let me talk a little bit more about these Wednesday night writing sessions. If you didn't see this before, your first reaction might be like, whoa, this is like I have like 11 tests, like a test each week. But I must emphasize, this is not a test because you know the questions in advance, okay? Like they're not like surprises. It's literally the same questions that you've known. And this second point I also cannot stress enough. Like, do not just be like, oh yeah, I know how to solve the problem, and then go in there and try writing it down for the first time. I 100% guarantee you will botch it, okay? So you must practice, like literally practice writing out your solutions beforehand, okay? This is the way that you'll, inevitably, potentially discover problems in your own solutions, figure out better ways to explain things, figure out like better layout on the page for your solutions. You should really practice beforehand so that really on Wednesday night, it's just like brain dead, you walk in there, write down your solution. Yeah? Do you have a question?
Can you tell me a little more about what we're going to do tomorrow in the option lecture?
In the optional lecture, I'm going to tell you some stories about proofs, some like historical anecdotes. We're going to talk a little bit about what are proofs. I'm going to try to give you some like tips on like finding proofs and writing proofs and like understanding what is a good proof and what are typical problems with proofs. Okay, good. So yeah, it's also very important that I'll talk about this also a bit tomorrow, but that your proofs are presented well. And in fact, all the homework problems, 20% will be reserved for presentation quality. Yeah?
Wait, so this is our homework, like this, when you hand in, when you write it on the Wednesday night, that like is the course homework. It's not like that is an additional.
Right, yeah, so so Thursday night we'll like on the web, or Thursday probably noon on the web, we'll be like, here are the problems of the homework, and you will, work on them like normal, and even like you should write down your solutions like on Wednesday, but like you will not turn in that paper. Instead, you'll come in on Wednesday night, write a solution to this selected subset of the problems, and like turn that in. Is it clear? Yeah?
What's the purpose of that system?
Well, one purpose of that system is, well, there's two purposes. One is it's a constant struggle in courses with turn-in homework to make sure that people really wrote the solutions themselves and they didn't copy. So in this way, at least we know you wrote the solutions yourself. It's also to eliminate some of the grading. So I mean, in previous years, it was like a nightmare scenario where like you would turn in your homework and the TAs would grade all of it, and it would take them like 6 weeks to like grade one homework, and like basically the students would never get feedback. So so you see right here, we're going to return your homeworks on Fridays, directly after Wednesdays, okay? Which mostly due to the heroism of our fantastic 14 TAs, but also partly due to the fact that they have less to grade. Yeah?
Does this add a little bit of time pressure? Like, what if your solution involved 2.5 pages of writing?
So we're going to make sure that the questions are designed so that there will not be time pressure for this. Yeah?
Can you elaborate on the 20% reserved for?
Well, partly this is up to the TAs, and I'll talk about it a little bit tomorrow, but in particular, homework solutions have to be well written in full sentences. I mean, it has to be moderately neat so that the TAs can read it, and there has to be a clarity of thought. I mean, your TAs have to be able to, proof is more like an essay. They should be able to read and understand your proof. It should not be, random correct, but like poorly structured mathematical facts. Yeah? You should ideally not miss a writing session. I mean, in particular, it's scheduled in the course, just like the lecture times, right? I mean, the times for this course are 9 to 10:20 on Tuesdays and Thursdays, Wednesdays from 6:30 to 7:50, and Friday recitations as well. Was that a question? Yeah.
What if there are like unavoidable reasons for not being here?
Like you break your leg or something?
Maybe somebody has an interview in the spring and they get flown out on Tuesday.
Well, I mean, ideally you should attend the writing session, but you can contact us. Yes?
Same random subset?
Yes, everybody gets the same random subset. Yes.
Is there any other, is there a way that we can type up our solutions? Since I really don't want to write them out.
No. Although, I should say, I mean, this probably affects only a very small minority of students. But if you have like documented accommodation issues from like Larry Powell's office, then of course we're happy to accommodate them. And in this case, please contact us. Yeah. We'll work it out. It depends on the case-by-case basis what the accommodation need is. More questions? Yeah, this is the most interesting topic of the. Yes?
I'm not sure if you said this already, but this is all like closed book. We don't actually get anything that we wrote beforehand.
Yeah. You should enter only with a pen. Yeah. Maybe a water bottle, because that room is very hot. Yeah? No, you will not need a calculator in this course. Well, actually, I mean, I could it potentially assist you when you're working out the solutions during the week, but like not for the. I assure you, you won't need a calculator. Yeah. Pencil is dandy. A nice pencil? All right, cool. Yeah. Highlighter, no. Okay, more questions? Okay. Additional questions, I mean, ask on the piazza. I mean, we want to get it straight. Okay, let's see. Homework policy summary. Again, go to the website to read the full policies, but I'll discuss some of them. Perhaps the main one is this. I mean, some of the problems are group problems or open problems where you'll be discussing with other people. The thing I must stress is that no written notes, be they like on paper or electronic, may be maintained after your in-person discussion. So in particular, like if you're working together with your friends on the whiteboard, you cannot like copy your notes off the whiteboard at the end and walk away. That would be maintaining written notes from your conversation. You should also erase the whiteboard. Or similarly, if you're like all sitting around a piece of paper, which is a little weird, but you should throw that paper in the garbage at the end of the discussion. Okay, it's supposed to be retained here. This also means like no discussion by email and no discussion by Facebook chat or whatever, because electronic copies of this are maintained in the universe. As always, you cannot Google to find the specific answers to the specific homework questions we ask. I mean, we try to choose questions that are really well designed to make you learn and to reinforce the material. So in some cases, the answers may be out there, but you're not allowed to search for them. Of course, you may search, books like those physical things or the internet to learn, general mathematical and computer science topics to help you understand. And although some of the problems is about collaboration, you should think about the problems before you start collaborating. In particular, this will also be mentioned on Piazza later, so watch out for it. But as always in science and research, it's important to record what your sources are and who your collaborators were and give them proper credit. So in fact, before every homework, there'll be an online form you'll fill out, which will usually be worth 1 point on the homework, documenting these. And before the first homework, we'll have another one that asserts, where you'll assert that you have read and agreed to the cheating policy on the webpage. Yeah.
Before you mean before Wednesday?
Yeah, before 8 days from now. So probably we'll post about it next Monday. So again, watch Piazza. I mean, it'll probably be a note about it on the homework as well when we hand it out on Thursday. Yeah. Mm-hmm. Yeah. Okay, I think that's it. I only have one slide with, I don't know, I thought I'd end with some keys to success in 251. I don't know, just some tips. Use the office hours and Piazza, please. I mean, wait, there's a whole slide left, dudes. Hold on. It's important. Find group members that you work well with. I mean, you're going to be working in groups for a lot of these problems, and this is a big issue. I mean, you want to work well with your group members. This is also important. If you're not happy with your group, and this happens inevitably, you should break up with your group. I mean, this Piazza thread about finding new group members will be active for the entire course, and it's not good to be stuck in a group that is not working for you. I cannot stress this one enough. I mean, I mentioned it before. I got to stress it again. Please, take it seriously. Practice writing the homework solutions before you go in on Wednesday nights. When you get your solutions back on Friday that are graded, don't just throw them in the garbage without looking at them. I mean, it's important to learn from your mistakes so that you can improve. And finally, it's a challenging course, so please embrace the challenge. And I'll see you maybe tomorrow.